Good morning, everyone. Welcome to another OGRA webinar. We are fortunate today to have Armtec and Hatch to present to us on Shamrock Lake Centre Culvert Rehabilitation. I will be your host and moderator. My name is Amin Menena. I'm the coordinator of technical products and research with OGRA and MEA. Some housekeeping notes before we start. We encourage you to put your answers in writing using the Q&A function throughout the webinar, and we will address them verbally at the end. But throughout the webinar, we have Doug with us, who will be typing in the answers to you as you go. So at the end of the webinar, if there's any questions that we couldn't answer them because of time, we will forward them to our presenters, and they will follow up with you with email. So it's my pleasure now to introduce our first speaker, Angelica Kieranas. She's the intermediate engineer, highways and bridges with Hatch. Angelica is a bridge engineer whose focus is primarily highway structures. Angelica completed her Bachelor of Applied Science in Engineering in 2015, majoring in infrastructure engineering with a minor in business. We also have with us today Hiba Ahmed. She's the Director of Business Development with Armtec. Hiba is a civil engineer graduate from Dalhousie University and has also completed her MBA from Wilfrid Laurier. She has over 19 years of experience in the infrastructure industry, holding different positions over the years from design to project management to sales leadership. With that, I would like to turn it over to Angelica, our first presenter. Angelica, the floor is yours.
Thank you. So I'll start off today with a bit of, I'll just go through the topics that we will be discussing. Starting off with some project background, followed by the challenges that we were faced in the design, then going through some of the options and our selection criteria. At which point I will go through the tunnel liner solution before handing it off to Heba, who will take us through the product details, the design challenges, some of the construction challenges, and then the conclusion, as well as some Q&A. I believe, hang on, I'm just gonna turn on my video here. I'm sorry, I'm having a bit of a few technical difficulties. We'll just proceed like this. So a bit of background. Shamrock Lake is located on Highway 11, about 31.5 kilometers north of Nipigon, which is about an hour and 45 minutes from Thunder Bay. So it is a relatively remote location, which poses some challenges for supply of materials. The existing structure was constructed in 1938, was about 76 meters long with a 4.9 meter span, 2 meter rise. That was a cast in place open footing culvert under about 16.3 meters of cover and had not undergone any rehabilitation since its initial construction. The concrete barrel was in particularly poor condition, and any concrete patching and crack repair would not restore the integrity of the culvert. So any rehabilitation had to address the structural concerns that were present. There was severe swelling and exposed rebar throughout. This photo was taken in 2005, and then this is the same location in 2016. So after 11 years, see the delaminations proceeded to spalls, and there was more exposed rebar throughout the entire structure. Additionally, there was wide cracking throughout and settlement of approximately 360 millimeters at the center of the culvert. Additional background constraints included the fact that this was a critical spawning habitat for brook trout. This led to a key requirement of the project, which was the maintenance of velocities within the culvert, as these were the same as upstream and downstream channels. There was the footing depth of the culvert was unknown, and so there was the risk of undermining the footing with any excavations at or below the footing shelf. Additionally, the excavation in front of the footing risked reducing the bearing capacity, and given the precarious nature of the structure and safety requirements, this was not ideal. Additionally, the high groundwater in the foundation soils pose a risk of sloughing and washout if the groundwater was not controlled during excavation. This was also located within the Nipigon Palisades Conservation Reserve. However, the right-of-way was excluded from the conservation area, but the right-of-way was particularly narrow at this site. So a permission to construct and occupy was granted, provided that certain design features were included in the construction. All of these features were related to fish passage and the maintenance of a nice fish habitat, including fish baffles and substrate retention sills, a minimum requirement for the embedment, an energy dissipation pool downstream, as well as a low flow channel. Now, in addition to the very narrow right-of-way and the location within the Nipigon Palisades Conservation Reserve, it was adjacent to the TC Energy pipeline with the edge of the prescribed area just outside the MTO right-of-way. So here, the blue line is the MTO right-of-way, which was located about 10 feet away from the edge of the culvert. The dashed red line is the edge of the prescribed zone, which was 6 feet away from the right-of-way. And then the gas line there I have outlined as the approximate location of the TC Energy pipeline. The replacement options examined were a precast concrete culvert box, a replacement bridge. We also looked at tunneling options and structural liners. The precast concrete box as a cut and cover was most well suited to meet the hydraulic conditions, as it would provide a structure either identical or slightly larger than the existing structure. However, there were numerous constructability challenges, including the excavation volume of the excavated material, which would need to be stockpiled for future use in backfilling the replacement structure. At this height, roadway protection would be challenging, if not even possible. And so a temporary modular bridge was examined for the maintenance of traffic. However, this was in excess of 60 meters long due to the high fill and need for benching. Because of the complex construction, it would likely require 2 construction seasons, pushing the need for a temporary modular bridge over the wintertime, which in Northwest region is not desirable. Additionally, the units required to support that overburden were incredibly heavy due to the need for a very thick top slab, wide haunches, and thick walls. These would also be very challenging to install. We did also examine the use of EPS foam to reduce the loading on the culvert and the weight of the units. However, this made no difference as far as the cost or the complexity of the construction. A bridge replacement would be an effective long-term replacement, however, is very costly and would eliminate challenges associated with future rehabilitations of the culvert under high fill. However, it's typical to avoid replacing culverts with bridges, and it had many of the same constructability challenges as the box culvert, including the excavation and the volume of excavated material, the need to maintain traffic using a temporary modular bridge, and likely resulting in 2 construction seasons. We also examined tunneling methods, either as a single replacement structure or in conjunction with a structural liner. We examined pipe ramming, jack and bore, and microtunneling. However, if any obstructions are encountered during the pipe installation and they can't be removed, this would prevent further advancement and may jeopardize the installation of the trenchless pipe completely. As the new pipe would have to be installed parallel to the existing culvert, which would result in an overall increase in the inlet or in the channel width, which would result in a decrease in water depth, which is not desirable given the constraints with fish passage. It was also, given the hydraulic situation, large pipes would have been required, and these are even more challenging to install given using trenchless methods. Using a smaller pipe in conjunction with a liner did still have the result of widening the channel. And given the valley-like topography of the site, extensive grading would be required to create stable embankments, which is the shot I have on the screen. So as a result, none of these were considered feasible for the site. And lastly, we get to our trenchless liners, which is the topic of discussion today. The liner pipe did need to be selected in order to maximize the hydraulic capacity and minimize the increase in velocities through the culvert. We did also have to ensure that the section was structurally adequate and to minimize excavation adjacent to the footings. We looked at arch shapes, which most suitably meet the hydraulic requirements, as they are wide at the bottom and provide the depth similar to the existing structure. However, the stress concentrations in the haunches was too high, and significant excavation adjacent to the footings would have been required to fit the shape in the host structure. Round liners are the opposite, which, as they most effectively carry the stress, but they do result in the highest increase in velocities. They did also require significant embedment to ensure that we could maximize the width, and that resulted in significant excavations below the anticipated depth of footing. Now we come to our Goldilocks solution, which is the elliptical liner, which most effectively balanced these criteria. So in summary, we looked at the precast box, which had constructability challenges as well as structural design challenges. The replacement bridge, which also had the same constructability challenges and was more costly. Tunneling replacements, which are high risk and high complexity and not well suited to meet the hydraulic requirements. And then liners, which was what we selected, which minimized the overall construction complexity. And lastly, I'll go through some of the design challenges specifically with the elliptical liner. Even though it does minimize the increase in velocity through the culvert, any liner does have an inherent effect on the hydraulic area as you're reducing it based on the size of the host structure. So the final design included a berm, which created a tailwater effect through the culvert to ensure that the velocities the impact of the velocities would be minimized. We also had to minimize the excavation adjacent to the footings and manage the risk of destabilization, by which we used provisions for dewatering the excavation to lower the groundwater table and eliminate the sloughing concern. And additionally, the shape selected minimized the overall excavation that was required adjacent to the footings. This site, we also had a very short in-water working window from June 1st to August 31st. So again, the construction was too complex for a single season to take place. And so we used a mud slab to ensure that the culvert could be left over the winter while the dewatering operations were not underway. The mud slab also prevented any washout adjacent to the footings, washout of the soil adjacent to the footings, and ensured a clean excavation in the event that the flow diversion failed, preventing any deleterious materials from being washed downstream into the sensitive habitat. Lastly, the maintenance of the flow through the culvert was challenging, as significant pumps were required for the maintenance of flow. And so the diversion pipes, you can see, were the contractor chose to support these up in the corners. And I will hand it to Heba to go through the challenges with the actual design of the tunnel liner plates itself.
Thanks, Angelica. Just going to share my screen here. Okay, so I'm just going to kick it off by briefly going over some of the steel liner options that are designed and supplied by Armtec. So Armtec provides a host of structural steel plate options for reline applications. Those include multiplate, bridge plate, and tunnel liner. And multiplate is a product that's been around since the 1930s, so it's perhaps the most known product on the market from the family of structural plate products. It's a profile that measures 6 by 2 inch or 152 millimeters by 51 millimeters deep, and is offered for shapes and sizes starting at 1.5 meters and up to about 6 or 7 meters in span. Next is bridge plate, and it's a deep corrugated profile that measures 400 millimeters crest to crest, and the depth of that corrugation is 150 millimeters. So as such, it's more suitable for larger spans, and we can make spans in excess of 4 meters and up to about 22, 23 meters in open span. I want to note that both multiplate and bridge plate are usually installed using a slip lining technique, where the structure has to be assembled on the outside of the host and then pulled into the existing structure before grouting in place. However, today we're going to be focusing on the tunnel liner plate, which was the product selected for the Shamrock Lake installation. And this product is offered in the size ranges between 1.3 meters and up to about 6 meters in span or diameter. So tunnel liner is a product developed specifically for relining and soft ground tunneling applications. It's ideal for rehabilitating existing culverts because it can be constructed from the inside. As you can see here, the profile is very similar to multiplate in terms of the pitch and depth of the corrugation. It measures about 180 millimeters by 52 millimeters deep. So the section properties are very similar to multiplate. However, the main feature or the difference here is that it has two flanges on each plate, and that's done to facilitate making the bolting connection completely from the inside without needing to access the other side of the installation. So this product is available in different thicknesses, which is dictated depending on the load demands for the project. The plates also incorporate a swedge detail, which is basically sort of a notch or a bend in the plate that makes it easy to complete the bolting connection across the circumference. Again, all done from the inside. The plate itself measures only 500 millimeters wide, so it can be easily carried by a member of the construction crew into the hose pipe. Each plate is corrugated, curved, and punched, and then bolted together to form the desired geometry. Here you can take a closer look at the flanges I mentioned earlier, and you can see the pre-drilled holes shown here in the picture. So it's really easy to make those connections without needing access to the outside of the structure. For pressure grouting, plates can also be fitted with these factory supplied 2-inch half couplings, and these are welded directly onto the plate at increments determined by the designer. The product itself is very versatile, and as you can see here, different geometries are available from full periphery to open bottom geometry starting at 1.3 meters diameter or span, and as I mentioned, up to about 6 meters in span. Non-standard shapes are also possible, and we can come up with a custom shape that minimizes the end area losses, obviously in an effort to minimize the overall effect on hydraulics. Design service life is a huge concern when it comes to design of steel structures in general, and it's important to note that there are several coating options available for providing different DSLs. So the choice of the coating or material depends on the environmental parameters found at each job site and on the required service life, which I want to mention is now a requirement in the CHBDC design of any buried structure. So I'm going to go over that a bit later. But all the coating options are outlined here. As you can see, there is a galvanized option that provides a design service life of anywhere between 40 to 50 years. The polymer coating is available and it provides 75 years of service life. And we also can supply an aluminum product, which is a marine grade aluminum tunnel liner plate, providing anywhere between 75 and 100 years of service life. That product is ideal for seawater or brackish environments, so it would be used quite a bit out east. For the Shamrock Lake project, however, the polymer coated structure was selected to provide the 75-year service life as required by the MTO contract. So the polymer coating itself is a thermoplastic copolymer coating that's applied in 3 steps. Step 1 is to sandblast the black steel to make sure there's no oils or grit on the surface. The second step is to apply a zinc-rich primer layer to each plate individually. And the third and final step is to apply the sprayed powder coat evenly to each plate, which then enters a very high temperature oven. So all in all, you're getting about 20 mils of coating for both sides. Here you can see the picture of the coating process after the application of the coating, and each plate is basically conveyed into the oven to be baked on. So it's done in a very controlled environment to ensure outstanding and consistent adherence. Once the coating is applied, obviously the plates are then conveyed out of the oven, and they are getting ready to be shipped to the site. I wanted to mention that the CSA standard G401 governs all the material fabrication, inspection, repair, and tolerances in manufacturing of all of the structural plate products I discussed. It also has the specification for the different coatings, including the polymer coated product presented here. And you can download a copy of this publication directly on the CSA website. As far as design, basically, as the physical size of the culvert increases, the structural design requires it to be designed in accordance with the bridge code. So in Canada here, the Canadian Highway Bridge Design Code, or CSA S619, is accepted across the country. And this is the bridge code that demands structures greater than 3 meters in span to be designed in accordance with Section 7 of the code, which is titled Buried Structures, basically treating them as buried bridges. So if you're considering a structure under 3 meters, however, these can be designed using AASHTO or ASTM, which follow the theory of ring compression. And extensive research was funded by the American Iron and Steel Institute in the late 50s and early 60s on ring compression design theory. And this method is now detailed in the Handbook of Steel Drainage and Highway Construction, which you can see a picture of here on the right-hand side. For structural relines, additional checks on grout pressures and how that measures up against the buckling strength of the liner plates are also completed. The bridge code uses references and resources from industry sources and subject matter experts to come up with a bunch of design checks using these rigorous equations to analyze each buried bridge. And this is done for all types of buried structures, regardless of the material type. Here is a list of all the design criteria that any buried structure would need to meet. And obviously we check for minimum cover, we check for the total thrust due to live load and dead load, as well as seismic. We calculate the compressive stresses in each structure. We calculate the wall strength in compression, as well as the combined check in compression and bending. And obviously, since these are bolted structures, we also check for seam strength. So some of the specific design challenges with this project are outlined here. First, when a reline is considered for a culvert structure, hydraulic capacity is often top concern. So as we're really just concerned with the flow rate discharge from the structure and aim to minimize any hydraulic losses due to the reduced size of the reline. For this reason, the horizontal ellipse shape, as mentioned earlier, was selected, and that structure measures 3.7 meters in span by 2.3 meters in rise. And it was designed to reline the existing concrete box culvert, which minimized the end area losses and maximized hydraulic capacity as it has a higher conveyance factor. The height of cover was also a challenge on this job. As Angelica mentioned, there's 16 meters or more than 16 meters of cover on the structure. And that posed a challenge for the structural capacity. For this project, we use high strength steel and as well as 3-gauge material to support this huge dead load. Also, the length of the structure is in excess of 70 meters, so it's pretty long. It presented another challenge due to the complications introduced with construction techniques. For most reline products, a slip lining technique is often required, whereby the structure has to be assembled on the outside and then pulled into the host structure. However, tunnel liner was unique in its ability to be installed on the inside, eliminating the need to figure out an effective way of slip lining while dealing with friction factors, dragging forces, and adequate equipment to pull a reline structure into the host structure. I'll go into the grouting process in a bit more detail when I talk about the construction sequence, but grouting pressures are also presenting challenges on any project. The design needed to consider the right lift size allowed based on the allowable pressure. For this structure, the grout lifts were designed taking into account the buckling resistance of the structure and ended up being done over 3 lifts in total. And since the invert of the existing structure was heavily deteriorated, Armtec also needed to design an invert beam to be welded at the bottom of the new liner for the structure to be blocked against and to support the shoring jack forces that fed through the sockets at the obvert. Another challenge was the incorporation of sill plates. As Angelica mentioned, these were designed by Armtec and based on the sill pressures that we were provided with. These were substrate retention sill consisting of 1/4-inch gusset plates that connected to the invert of the structure using angle brackets and the existing holes in the tunnel liner plate. So now talking about the construction sequence, the plates and required hardware arrived on site in bundles, as you can see on the left-hand photo here. After the contractor sorted through the plates and stacked them into the order of installation, they proceeded to build an access road down the steep angle off the side of the structure and use bobcats to drive these plates down to the culvert location. To prep the site for installation, the crew dug a pit and installed a pump on the upstream side that pumped water down a pipe coming on the side of the structure. And once the dewatering setup was complete, the crew then proceeded with plate assembly, following our plate assembly guidelines, which you see a snapshot here on the right-hand side. This specific structure consisted of 8 plates per ring, and the first ring was assembled by placing square shoulder bolts into the square holes in each of the 5 holes on each plate, as you can see on the bottom left-hand picture. We instructed the contractor to ensure that the bolt heads are on the exterior face of the liner plate. And next, speed clips were secured over the threads to hold the bolt into place before the next plate was brought in with swedged or hinged end to be nested right through that bolt and into place. And finally, hand tightening of the nuts was completed. This process was repeated until the first ring was in place. Then the crew proceeded with successive rings in the same manner until the entire structure was assembled. Once all the plates were assembled, final bolt torquing is done to Armtec's specified torque range, which is in the range of 135 to 170 Newton meters, and torque checks follows full assembly. Typically, we require, or the contract requires 95% of select random 10% of the bolts to meet the required torque values. Next, the contractor proceeded with welding the W-beam to the structure invert and proceeded to install the house jacks feeding through them through that 12 o'clock grout socket. These grout jacks or house jacks were spaced at 4.5-foot centers through the length of the structure. The left-hand photo shows we used some concrete cinder blocks underneath the invert of the liner to keep a gap underneath for grout to flow freely and under the invert of the reline. The grouting process is usually the trickiest part of the project, in my opinion, and the contractor needed to ensure that each lift of grout was allowed to fully cure for 24 hours before the next lift was poured. It was also very important to monitor the grouting procedure to ensure that all the gaps have been filled before proceeding to the next lift. For this structure, lift heights were determined based on the composition of the grout material, the size of the structure, and the location and increments of the bracing. The first lift was the most important to control and monitor and usually has the smallest pour height. As shown on the drawings, the first grout lift was around 550 millimeters. And once that was set, subsequent larger lifts of the second and third pour were done at 800 and 960 respectively. We always recommend on our drawings to use flowable lightweight grout between 2 to 5 MPa due to the flexible nature of the structure. This is a very important point that I want to make here, as there are usually concerns with using higher strength concrete for the grout, as that introduces stress concentrations when using these rigid grout mixes, and these can cause additional load demands on the structure for which it wasn't designed for. So I just wanted to highlight that point, as I know we get this question very often. Armtec also suggests additional grout port locations to ensure room for venting, buoyancy control, and inspection of the full void coverage. This is just a picture that shows the inside of the structure after the grouting process was complete. Once their crews finished grouting, they would remove their grout nozzles from the ports and use these supplied threaded grout plugs to close off the ports. We always remind the contractor before completing the step to check grout elevations, check grout consistency, monitor and clean any grout seepage before the material is cured, and implement appropriate venting during the operation. So all in all, this was considered a huge success. And the benefits of using Armtec's tunnel liner plate are summarized here. So basically, tunnel liner was an ideal product for this application due to its ability to be installed inside the host structure with no disruption to traffic. So no detours were required here. Using this product introduced huge cost savings as there were no need for costly excavations of this deep embankment or demolishing of the existing structure. The horizontal ellipse shape optimized hydraulic conveyance of the culvert. And the material is lightweight, only weighing anywhere between 15 and 40 kgs. So it can be installed without any heavy equipment to lift these in place. Also, the modular and stackable nature of the plates enables cost-effective shipping to remote sites. These usually nest and ship all on one truck. And one of the most important aspects of this is that it's a true structural liner. So it's designed to handle all of the loads without relying on any strength contribution from the host structure. Last but not least, structural plate steel products are one of the most environmentally friendly materials used in construction as they are highly recyclable and have the lowest carbon footprint in the industry. Before we move on to the question period, I just wanted to put up the slide to show all of the different products that Armtec supplies for trenchless applications. As you know, Armtec manufactures both steel and plastic products, and this table highlights both offerings for reline applications and summarizes some of the key values or factors affecting your selection criteria. So you can see here an outline of each product, the material type, coating availability, service life, size limitations, as well as the Manning's end value, which is important when you're considering conveyance structures. And all this information can also be found on Armtec's product brochures and website. So if you have any questions about those products, please feel free to reach out. And with that, I will hand it back to Amin and we'll take some questions.
Thank you so much, Heba and Angelica, for your on-point presentations. So we can start taking questions right now. Angelica, you can go ahead and turn on your video feed. The first question is, what size storm event were the bypass pumps designed for?
No, that's working. I'm just looking that up. I believe it was just the 2-year storm. However, in this case, it was a fairly sizable 2-year storm. If I'm remembering correctly, the time to peak was very short here, given that it was just on the edge of a fairly significant hill before the highway. So the concern wasn't so much about the conveyance of the flow, but was more about the ability to react to the flow if it did happen. But I don't have the numbers offhand.
Okay, thank you. And another question is, what end treatment was designed for the inlet and outlet?
At this site, we just had the square end treatment. We also had specified that some concrete repairs be done to the face of the culvert to produce a more long-term nice looking structure, really. But yeah, with the liners, you want the face of the liner pipe to be flush with the host structure. So there was no beveled ends or anything like that at the site.
I see. The next question is, are there only standard shaped or to choose from, or can custom sizes be prepared?
Yeah, that's a good question. As I mentioned, I put up a slide that shows all of our standard shapes, but we can also customize the shapes to fit the whole structure as close as possible. We basically try to marry the liner to the existing structure while keeping a minimum gap between the host and the liner to facilitate grouting. But yeah, custom shapes are very possible.
Thanks, Iba. The next question is asking what is a general rule of thumb for the cost difference for each material?
It really depends on the size and the shape. Um, but really, some of the larger structures might not be feasible in, let's say, if you're looking at a round structure, you can either use BOSS 2000, which is our plastic HDPE liner, or CSP. You can go either way, depending on the design service life you require and the durability needs. What's going to break that race is basically the size of the structure. So beyond a certain size, it sort of flips into the steel becomes more economical.
Mm-hmm. And I guess to add to that, for the same size and material, would the shape play a factor? I guess for a circular shape, would that be more cost effective versus other shapes?
For circular shapes, if we're talking about steel, the cost would probably be comparable. It might be on the higher side if it was an arch shape, because that's an additional operation that we have to do to arch them. However, it's mainly the choice between the two different shapes have to do with the conveyance, and one shape is more hydraulically efficient than the other.
I see. The next question we have, and we have quite a few questions here. The polymer coating provides a 100-year service life in one product and only 75 years in another product. Do you have any comments on why is that?
The polymer product, basically, we've done accelerated salt spray tests on these products to rate them for these service lives. And it highly depends on the chemical composition of the site. So you can put a product on a site that has hard water and high pHs and whatnot that can last can last a shorter duration than in another site where those parameters are not prevalent. So really, it's designed based on the site parameters, the chemical composition of the soil and the water. And as I mentioned, now this is a requirement of the code. So we would look at all these parameters and design the coating based on the service life required.
I see. So what steps were taking to protect the coating, given the grouting process, equipment in and out, and the river rock used as the internal bidding?
There was nothing really used in terms of protecting the coating from the grouting operation. We have not seen that these were an area of concern with grouting. So basically, after the installation, the grouting is applied on the outside, and once that seal is there, there's no concern of corrosion on that side. The bedding, however, might be something that has to be looked at. And on this specific site, I'm not sure if there was any consideration on the bedding. Maybe Angelica can comment on that. But we have not taken any measures from the supplier side.
Angelica, do you have anything to add? No? Okay. I have a question for me personally. Uh, Throughout your product installations and different projects, have you had any specific challenges with the host pipe that you had to treat the host pipe before you install the reline and grout it?
That's actually a really great question. It's something I didn't touch on in this presentation, but at this site in particular, we did actually have a requirement to go through the hose pipe and just sort of use hand tools to take off loose bits of concrete and to fill voids. And now the reason we specified that was just to ensure that there would be adequate contact between the hose pipe and the liner, that you wouldn't get kind of delaminated bits of concrete that were stuck between the grout and the hose pipe. And then additionally, to fill voids, because we didn't want to have just a black hole where all this grout was flowing and we weren't able to control it. So those were the two things that we did at the site to kind of prepare the structure. Now, they're not exactly strictly required as far as the structural capacity of the new composite structure, but we felt it was best practice to proceed in that manner.
I see. And another question relating to that. So are those relines always structural?
Not necessarily, and that basically is one of the design considerations we have to go through. We need to know if this is sort of a facelift reline or meant to be a structural reline. And if it's a structural reline, we design it to take all of the loads, assuming that the host structure is not even there. If it's a facial reline just to prolong the service life of the existing structure, then obviously it will be a more economical design.
I see. So the next question is asking, during the grouting phase, how does the contractor monitor and check the grout levels behind the liner?
So as I mentioned, there are grout ports installed at certain increments throughout the length and at certain points across the circumference. And some of those are used as monitoring stations or to be able to see what's happening on the other side. That's used to monitor some of the techniques used for grout.
I see. Thanks. So I guess to capture that, if I understand it correctly, so basically you know the volume of the grout that you should be pumping for each section, and you know how much pressure that should come out of it. And when you get that pressure, you know that you match it with the volume, and you know that you're doing a good job. If the pressure
Correct.
is low, then you know there's a loss somewhere, right?
Yes, that's in conjunction with actually visually looking through a grout port and making sure that the height is at the right level.
I see. So due to the length of the culvert, was this job site considered confined space?
I'm not entirely sure. I can say that we didn't have any provisions for it being a confined space included in our contract, but that would be the responsibility of the contractor to ensure that the aspects of the construction are in accordance with OSHA.
I see. And you mentioned that the grout will be installed in multiple lifts. Do you have to wait for the grout to harden, or how long between the installation of grout lifts?
Absolutely. We put that right on our drawings that each lift has to cure for 24 hours minimum. So it does, you have to wait for it to cure before applying the next lift.
Mm-hmm. So is there a concern with this stream debris load being deposited in the structure as a berm was introduced to, let me read that again. Is there a concern with the stream debris load being deposited in the structure as a berm was introduced to slow the flow?
So that's again another interesting point. There's only so much that we can do with these structures as far as implementing means to slow to get the flows where we want them. But after a while, the channel and the natural environment will do what the natural environment wants to do, and there's no way to control that. So in theory, yes, there will be some additional bedload deposits, but that'll all, over the years, if a bedload deposit happens in the stream bed, it'll get washed away by another bigger storm. And this is a natural stream process, and it's just the way it is. So there's no provisions for that in the design.
I see. And the next question is for you, Hiba. You mentioned that the steel with a lower carbon footprint than concrete. Do you know by what magnitude the difference is?
There has been some studies done on this, and we have an environmental product declaration that can be downloaded off of the CSPI website, Corrugated Steel Pipe Institute, which does a pretty good job comparing the footprint effect.
Thanks. What type of channel treatment was used for the outlet end?
I'm unsure with what kind of channel treatment, what that means. But we, like I said, we had a berm downstream, and then we also had a fish ladder beyond the actual right of way that we were allowed to put in because it was in the conservation area, just to kind of mitigate the impacts of the construction to the fish. I hope that answered the question.
I think so. And to the person who asked, if that doesn't address your question, please type it with more details and we'll get to it. So the next question is, are there any specific inspection and maintenance, I guess, instruction or best practices from your experience that should be followed to ensure the structure will reach the desired service life?
So any structure really will have to abide by the inspection requirements at the municipality or the DOT. So whether that's OSIM every 2 years or whatnot, but we obviously recommend that all structures be maintained and part of that program, whether that's just sort of inspecting to see if there are any long-term effects on the structure due to bed load or whatnot, or any cleaning requirements that has to happen to make sure that they do reach the end of their service life. But really these structures in general, structural plate structures in general, require very little maintenance throughout the service life of their installation.
Thanks, Hiba. And relating to that, I guess, is the liner designed to carry the existing concrete as a dead load?
The dead load is considered the height of cover starting at the inside corrugation of the liner and up to the finish grade. So that obviously includes the depth of the concrete, but we are assuming that that is part of the soil, that's the dead load on the structure, because I mean, in the grand scheme of things, the thickness of that slab is not that much.
Mm-hmm. Can this system accommodate culvert curvature in the alignment of the hose pipe?
Not sure I understand the question. Can you read that again?
Can this system accommodate curvature in the alignment of the hose pipe?
Yes, so if the host pipe is an arch shape or a curved shape or even a round shape, obviously, again, we can do standard or custom shapes to accommodate those curvatures. We basically treat it as an outside clearance box that we have to pass through and try to be as close as possible to the host structure geometry, but again, allowing a minimum gap there for grouting.
I see. So I guess would that make sense? Would that rule out the option of slip line versus installing the reline in the culvert? If it's straight versus with a curved alignment.
Oh, are you talking about horizontal curves?
I think so.
Okay. Yeah, definitely. That's something that has to be identified at the beginning because we need to design and allow for that. What we do is we manufacture in our plants elbows that are basically two pieces welded together that get shipped to site as an elbow, and those can get installed to accommodate any kind of horizontal curvatures.
Thank you, Hiba. So it was noted that an I-beam was welded to the bottom of the culvert on site. Does this compromise the polymer finish?
No, I mean, whenever you do any sort of field fittings or welding on site, you can use touch up on the polymer coating if that was affected. So that was done here. But no, the beam really was needed there to support the house jacks to be propped up against the obvert. So that was installed with welded to the invert of the structure and then touched up.
Thank you. I can see just some people are typing comments with feedback, with excellent information. So thanks. So one question, I guess it's more of a side note. How long did the environmental approvals take for you guys? I guess it's an Angelica question.
Yeah, that's not something that I was particularly involved in, but I know it wasn't overly long. Given the detail and preliminary design phases were quite lengthy, it wasn't of note in this project.
Mm-hmm. So does the different coating systems have variable flow friction characteristics?
Not really. The coating systems are really thin in comparison to the corrugation depth and profile. The friction system really relies more on the corrugation profile than the coating itself, and is translated as a function of a Manning's N.
Mm-hmm. That makes sense. Is there a need for bonding agent between grout placement to avoid separation?
We have not seen that in our experiences with all the installations that we've done. We have not seen the contractor use a bonding agent.
And in the 70 years, can this culvert be removed and replaced with a similar new product?
I guess in 75 years, this can be a new contract with new parameters, and depending on what the owner wants to do, replacement versus reline. Yes, I guess if you're relining a reline, you're again losing more end area. So I would think that at 75 years, I'd be long gone by then. But you know, it would be more of a replacement than a reline.
So, so replacement. Would there be any structural challenges when? Would you just replace the grout when you're replacing the grout, I guess?
Well, with replacement, you're going to have to dig out the entire embedment or embankment, as well as the existing structure and the reline, including the grout. So you're really digging out everything. And with that much cover, it's going to be a challenge with this much cover for sure.
And since it's such a long service life or design life for this product, in your experience, have there been any projects for replacement of a reline?
I have not lived to the day yet. I mean, I'm not that old, but I can't tell you.
Well, that's good. That only testifies for how for the integrity of this product, I guess.
Right.
So a question for you, Angelica. As a consultant, what was the most challenging part of this project?
Probably, I would have to say dealing with the unknowns of the footing. We had foundations information, which were or borehole information, which was limited, and then dealing with the concern of the precarious nature of the structure, and trying to limit excavation, and also simultaneously speccing dewatering so that the contractor would be aware of the precarious nature and the severity of it. That we weren't just trying to say, you know, this is probably fine, but do it anyway. It was actually, this is a big deal. You should really listen to us this time.
Mostly the risk assessment and all of that part.
Yes, and ensuring that the contractor, or doing our best to ensure that the contractor was aware of the risks associated with the construction.
So how much did the settlement in the hose pipe affect the span and the rise?
That was another thing that we did have to deal with during construction. During design, we did specify a survey of the existing pipe prior to procurement, because we didn't. We wanted to ensure that the pipe wouldn't get to site and, oh no, it doesn't fit in the hose structure because you've got the settlement mid-length. So we did have the contractor survey the whole pipe to ensure that this would fit, and we did verify it based on their survey results. In this case, the other challenging part was the outlet was actually higher than the inlet, and so we had very careful detailing to ensure that the size of the pipe would work and that the inverts would be appropriate for the velocities that we needed to maintain.
So in your alternative, I guess when you were considering different alternatives for this project, did you include or did you do an exercise for life cycle costing to select your final solution or alternative?
That was not part of our scope to undertake that. There had been another reline on a culvert's. There had been another couple of relines, and that was what the client wanted us to look at. So,
thanks. So for this particular project, I know you touched on it, Angelica. You touched on all the different alternatives, but just to come back to that, would the slip lining with the multi-plate be a viable option as well for this project?
so I can touch on that too. I know Heba already did a little bit in the presentation. Given the challenges with the narrow right of way and the need and the limited laydown area, again, also the fact that the structure is 76 meters long, slip liner, I would say it would be viable, but considerably more difficult in this case, especially given the weight of the structure as you near the completion, to be pushing that whole 76 meter long steel pipe in through the culvert would be quite challenging. And that was part of what we had faced in design as well.
And another question again for you, Angelica. Can you comment again on where was the water course diverted to?
The water course, as the best of my understanding, there was hoses supported in the corners in the haunches of the culvert, and that's how the contractor chose to control the stream flow during construction.
And again, to you, Angelica, or to what extent or how was the risk of cost increases managed through the contract given the unknown surrounding footings, and how did you balance cost versus safety, I guess?
Our best idea was to just kind of try to avoid excavation by the footings, and that's how we, I think, most effectively managed that risk.
I'm just reading through some questions. So the question is mentioning the beam and the structure used to support the jacks. What was the beam structure attached to?
So as I mentioned, the beam was installed and welded to the invert of the horizontal ellipse at the bottom. And then the house jacks basically were resting on that W beam to be supported at the bottom on the beam. And at the top, it's basically being propped up against the obvert of the existing host structure. So that way, it's basically bracing the structure up against the beam while there is fluid pressures from the grout during the grouting operation so that the structure doesn't float.
All right, thanks, Heba. So we'll take one more question since we're one minute away, and we will wrap this session up. With the new smaller culvert, what makes up the reduced hydraulics opening?
So we didn't really make up the reduced opening. What we did was, as I said, we had an energy dissipation pool at the outlet, and then we also had a berm constructed to the same elevation as the inlet, creating a tailwater effect through the entire culvert, which the hydraulic engineers told me was sufficient to mitigate the increase in velocities and to ensure that the as far as the hydraulics, as far as the opening and the conveyance, we had no issues. It was purely the velocities that needed to be addressed.
All right. Thank you, Angelica. And with this, we'll wrap up our session today. I would like to again thank Armtec and Hatch for sponsoring this webinar. And would like to thank Hiba, Angelica for presenting and sharing their experience and knowledge. And Doug, Mark, and Liz for being in the background answering questions. This webinar was recorded and will be made available on our YouTube channel, so stay tuned on that. All of the questions that we couldn't get to, we will forward them to the presenters and the panelists to answer them off the air through emails. So that, thank you so much and enjoy your day.